All right, so I want to work out a problem with you, and we haven't even quite been given all the information. So it says use the fact that the world population was blank million in 1950 and blank million in 1960. So let's actually go Google those and get our numbers. So it says world population in 1950 looks like roughly 2.5 billion. Let's go back to our notes and we can translate that. So 2.5 billion should be, let me switch sizes here, should be what, 2,500 million in 1950. And then let's go back to Google and see what it was in 1960. And we come up with 3.03. Let's round to 3.030. 3.030. We'll round down slightly so our numbers will be a little bit below. So we'll say 30. Whoops, it's a little hard to squeeze this in. Uh-oh. Yeah, I had a different number before, but I'm blocking it. We're going to use 3030. There we go. Million in 1960. So we're asked to model the population of the world in the second half of the 20th century. We're told to go ahead and make the assumption we need to make to be able to use our exponential model. We're asked to find the relative growth rate, and then we're going to predict the population in 93 and 2020. All right, so we need to write down some of our basic setup. So first off, let's go ahead and say, look, let's let t equal time. And our basic unit is going to be years. So I'm going to write down in years. And let's let t equals 0. Let's let that represent 1950. We have to have a starting point. Okay, we're also going to let p of t equal the population. We're working in millions at time t. It's really good to label everything and be very clear for yourself and others exactly what's what. Okay, so we assume, let's maybe get a highlighter here. We're assuming that the growth rate is proportional to the population size. And so that immediate assumption tells us that we know that dp dt is equal to k times p of t. And that you now know that, well, p of t, our population, has to look like some p naught e to the kt. And so the question here, there's sort of two details that we need to figure out. Let me erase this and try that again. We need to figure out what's p naught, and we need to figure out what's k. And once I've got that, then I can answer all the other questions. And so you need to realize that, well, p naught is just p of 0. That's the population in 1950, which we're assuming is 2,500. Okay, so we got that. Check, that's good. And so now we can say a little bit more. We can say, okay, p of t is now 2,500 e to the kt. And so now we're left trying to figure out what k is. And to do that, I want to use the other data point. See, I know something. I also know that the population in 1960, which corresponds to p of 10, we're assuming that the population in 1960 is 30 million. All right. And so I can view this two ways. On the one hand, I just know that p of 10 is 30. On the other hand, I know that p of 10, let's slide this over, p of 10, I can plug 10 into this formula. And so p of 10 is 2,500 e to the 10 times k, or k times 10. I'm going to switch it and write it 10 times k, but you understand 10 is playing the role of t. Okay, so now I'm going to sort of ignore this part and think about this relationship. And so I get 2,500 e to the 10k is 30. solving for k, this is something you can do just with basic algebra. So you get e to the 10k is 3030 over 2500. And so I'll take the natural log of both sides, and so I get, let's actually do that to the side here. So I get natural log of e to the 10k is just 10k equals natural log. Let's cancel this 0 there. And so we can say natural log of 303 over 250. That's almost there, so k is 1/10 the natural log of 303 over 250. Okay, it'd be nice to have an estimate for k. Yeah, that's a precise number, but in these problems we need to be able to estimate it. So I'm going to switch my screen to my Mathematica app, and what do we have? We had 30, and we were dividing by what? 2500. So let's close those up. Before we run that, let's go back and make sure that I had it right. Oh yeah, we actually canceled a 0, I guess, so it doesn't matter if I do or not. I will, just so it's exactly, whoops, the same, whatever. I didn't. And then I want to divide that by 10, so I'm going to add another 0, right? So this is what I get before I divide by 10. I can't zoom in anymore, so I'll just add another 0. So 0.9192272, let's write that down. So this is going to be 0.0192272 is our rough decimal approximation. And so now we've got a precise formula for P of t. So P of t, we know, is 2500 e to the 1/10 natural log of 303 over 250 times t. There's the precise formula for my P of t. And now I want to estimate the population in 93, that corresponds to 43, and the population in 2020, that corresponds to 70. And so let's go ahead and switch back to Mathematica, and then we can actually program in our P of t. So let's see, we can make a new input cell, and we can go ahead and define P of t just like you guys did in lab. I need to do underscore colon equals, and I want to do 2500. I'm going to do times, I want to do the number e raised to the parenthesis. I'm just going to use our decimal approximation, so 0.0192272, that's my k, times, let's actually put that inside there, times t, and that should do it. So we're going to evaluate that, and now we're going to ask Mathematica to please tell us P of 43, and let's see if it works. We got 5714, so we'll round it up to roughly 5715, and so we can say, okay, this is roughly 5715 million, or 5.7 billion, right? 5.7 billion people in 93. And then the population in 2020, we can easily run that now. We can just ask it, instead of 43, let's ask it, let's ask it to compute. Let me see if I can slide that over. There we go, P of 70. And I get out 9604, so 9.6 billion, 9604 million, or if you want, 9.6 billion. So that's what our model estimates. Now let's Google it and check it. So I'm curious, what's the population in 93 and then 2020? So we guessed 9.6 billion and 5.7 billion. Let's see. So we can go back to world population in 1993, and we get 5.5 billion. And look at our model, we had 5.7 billion. So really very accurate prediction just based on those two data points. And realize too, 93 is quite a few years out from our last data point. We're looking 33 years ahead of 1960, and we're still pretty accurate Now let's see how we did with 2020, because that's a pretty big jump for this model. I don't know how accurate it's going to be. Let's see, 2020. We get 7.8 billion people. So we really overshot. And if you think about it, that actually makes sense. And this is sort of the sad reality of the world that we live in. But there's people aren't very nice, and there's a lot of very bad things. There's disease, there's war, those kinds of things will pull the population down from what our model will typically predict. So anyway, our model says 9.6, but in reality, it's only 7.8 billion. So we're a little bit behind of what the model would suggest. But nonetheless, this is the answer to those questions. We were asked to find a model, which we did. Here's our model. And then we use that model to estimate population in different times. Notice I had to use the natural log to be able to solve this equation for k and get that growth rate constant. So, all right, great job. We'll move on to example 2 when you're ready in the next video.